model from a previous exercise, we'll build several compensators and use error limiting at the compensator input to control system behavior. The results are very similar to the strategy of setpoint slewing, which was covered in a previous video. The difference being that with setpoint slewing, system behavior is controlled and limited externally by applying a function at the setpoint input, such as smooth step or smoother step, whereas with error limiting, system behavior is controlled and limited internally at the compensator input. For these examples, we are adding the restriction that the plant input can't be negative and it can't exceed 1 over the plant gain. This gives us a plant output in the range of 0 to 1. Let's build the compensator now, specifying exponential output and 90% in 18 steps. This is as fast as we can go while remaining within the plant input restrictions that we added for this exercise. Copy-paste the coefficients from the data window into the spreadsheet. The compensator coefficients appear here with an integrator and a plant model. As we can see, we do indeed achieve 90% in 18 steps. 18 steps, 90%. And the planned input is in the range of 0 to 1. Right there. Notice how the compensator gives an initial big push in the positive direction and then recoils in the negative direction and then settles on 1 over the plant gain as expected. Here's the initial big push, the recoil, and settles at 1 over the plant gain. Now we will build a compensator that achieves 100% in one step. This may appear to be ridiculous, but it is possible under restricted conditions. Copy-paste the coefficients into the spreadsheet. The strategy is using error limiting right at the compensator input. This is very similar to setpoint slewing, the difference being that we are now clamping the maximum error right at the compensator input. And you can see the error clamping right here. Initially, we are limiting the error to 10%. We can see that the disturbance at the plant input is mostly contained, but the problem is the plant input overshoot at the end of the ramp. Here's the overshoot, almost 8%, and that appears right here. As with setpoint slewing, one idea might be to allow a small buffer at the setpoint extremes. Let's try limiting the setpoint to 0.95 instead of 1.00. Now the plant input remains in range. Let's adjust the error limit to find the maximum performance. To summarize this strategy, we're using a very aggressive compensator that achieves 100% in one step on its own, and then controlling the system behavior by error limiting at the compensator input, and limiting the set point to a maximum value slightly less than 1. This strategy achieves 100% of the maximum set point in 8 steps, but the set point is restricted to a little less than 1. Let's try using a slightly less aggressive compensator, say exponential 90% in 3 steps. Copy-paste the coefficients into the spreadsheet. We now see a linear ramp followed by an exponential with no set point restrictions, achieving 93% in 8 steps. Here's the linear ramp with a little bit of exponential at the end. Eight steps, 93%. Compared to the baseline compensator of 90% in 18 steps, that's a significant improvement. All of these systems involve plant inputs that are abruptly manipulated. Let's revisit each system with a focus on having a smooth, increasing plant input. Let's review quickly. Exponential, and here's the plant input. And here is the plant input for the second system and the third system. Revisiting the exponential 90% in 18 step system, we will now show an exponential ramp on the set point and see what happens. The plant input is now smooth. There's the plant input there. We are able to achieve 90% in 22 steps, which is not a bad trade-off to get a smooth plant input. As with set point slewing, we will use the same exponential ramp set point system as a baseline. So let's adjust the remaining plots so that they achieve 90% in 22 steps. All the systems are now achieving 90% in 22 steps. Here are the results. Here's the plant input for the second system and the third system. The exponential system is the only system that has a smooth plant input. Both of the error-limited systems have distinct wiggles at the plant input. Here and here. No matter how much these systems are slowed down, these wiggles will always be present. From the perspective of smooth plant input, set point slewing with smooth step and smoother step were much better. Well, we had fun exploring error limiting and the impact upon plant input and plant output. This concludes today's video. Thanks for watching.